Welcome back. We have been talking about how intelligent agents or intelligent machines need to be able to represent facts about the domain that they are operating in and reason with them essentially. We have also said that all this activity is not going to be in a standalone fashion, but it is going to be situated in a domain essentially. And we are going to look at reasoning, and we are going to look at reasoning from the perspective of logic. And the question that we are now trying to answer or is as to how do we decide as to what are going to be the inputs to our reasoning algorithm, what are going to be the representations over which our systems will reason. Now, of course, the representations are going to be about the domain that you are operating in essentially. Okay. So, we saw in the last couple of videos that the domain that we are operating in is in fact made up of some very tiny particles acting in concerts together. So, some bunch of particles is there as a human being, another bunch of particles is there as a tree, and so on. So, of course, we would want to represent things at that level of detail. So, let us discuss that a little bit as to what are the domains of reasoning that we want to build for our intelligent agents. So, while the real world that we want to reason about is indeed made up of collections of fundamental particles, whatever they are, we do not know what the fundamental particles are. Those fundamental particles cannot be the elements of the domain that we use for representation and reasoning, and the reason for that is that they are simply far too many of them essentially 10⁻27 atoms for one human being. And if you want to talk about a class of students, just imagine the amount of information that you would want to represent. So, if there are 30 students in a class, then you want to just talk about 30 students and not 30 into 10⁻27 sets of atoms. Even to describe a grain of rice would be difficult. Instead, depending upon the focus of study, one can represent things at the level of atoms or molecules or biological cells or animal organs or living creatures or societies of living creatures. So, we want to represent things at an appropriate level essentially. Each domain of study defines what is called its own ontology. So, we said that ontology is in some sense the study of being or the science of being essentially, what is out there essentially. And we also said that it is a explicit specification of a generalization essentially, that we want to decide what are the categories and the concepts that we are going to be talking about. So, the choice of predicates. The logic community, and in the first half of the course we will focus more on logic, is focused on proofs essentially, that if you give us some set of facts, what else can we prove from those set of facts. So, they are concerned with properties of logics like soundness and completeness and consistency and decidability. They are not really concerned about representation, they do not care. Like mathematicians, they work in the abstract, they do not care about what is it that you are talking about. They say, okay, you give us a set of sentences and we will tell you what other sentences follow from that. So, they work with arbitrary predicates, they invent predicate names as and when they need. The predicate names that you will see in logic textbooks are usually some words from English or some other natural language, depending on what is a language that you are discussing things in. But the problem with natural languages is that they are rich, they are expressive. The same thing can be said in many different ways essentially. So, for example, I can say A loves B, which is the first thing that I have said in a first order logic like language, which we will study. Or I can say A adores B, or I can say A dotes on B, I can say A is in love with B, and of course, maybe countless other ways of saying the same thing essentially. If you are going to use natural language like English to decide on what are the predicates that we are going to use, then we are going to be in for trouble. Because whenever you have predicates like loves and adores and dotes on and in love with, you will need rules to be able to connect such facts that A loves B to some other fact, that if A loves B, then A cares for B, or whatever. I mean, or A will buy B a present, or whatever the case may be. You may want to connect predicates with each other. So, the more the number of predicates that we have, the more the number of rules that we will need, and because we will see that logic is a formal thing, it does not concern itself with meaning, only with form. If I can match a pattern of a rule uh, with something, then I can infer some consequent. So, the more the number of predicates, the more number of patterns that rules will have to have. So, there will be an explosion in the number of rules and in the complexity of the theorem proving algorithms. So, we will see that logical generating proof is also called theorem proving. So, how do we choose predicates? The domain D. So, when we say that we are talking about first order logic, which is what we will spend most of our time in, we will say that a domain D is made up of a set of individuals, and that is our domain, and the logic talks about relations between these individuals. So, the predicates that we define will capture relations. So, relations between individuals, for example, Sumedha is a friend of Shreya. It will define categories, for example, Socrates is a man. It will define relations between categories. So, for example, if X is a deer, then X is a mammal. It will capture relations between named relations. So, more than categories, binary relations, for example, or higher order relations. So, for example, we can say that if X is the brother of Y, then X is Y's sibling essentially. These kind of things can be captured in logic essentially. So, depending on what are the kind of predicates we choose, we will have to add such rules to our logic essentially. So, inference involves traversing from known to unknown. So, we know some things and we want to infer something. So, if I say Anil is the brother of Seema, then I want to infer that Anil is Seema's sibling essentially. If you know that he is the brother, then you want to infer that he is the sibling, and that is the kind of stuff that logic allows you to do. Rules of inference will facilitate this level. So, this could be a rule of inference that we have here, that if X is the brother of Y, then X is a sibling of Y. The more the number of predicates, as we said, the more will be the number of rules essentially. So, how should we choose this set of predicates, so that our reasoning becomes tractable and computationally feasible essentially. So, that our representation is compact and canonical in some ways, that we do not want to say the same thing in many different ways. We would like to have a canonical set of predicates which represent the core concepts. And if we are talking about, let us say, input in English language or Hindi language, then we should learn to map language onto those canonical set of predicates. This idea is not new. It was explored in the late 70s and early 80s. So, more than 40 years ago. It has kind of ebbed a little bit, but we will see. We will look at those ideas a little bit and hopefully convince ourselves that there is a need to do something like that, to find a canonical conceptual representation which is not as rich as the kind of words that we use in natural languages, which is something more compact. We will look at some of that ideas, this thing. And the goal is that we avoid a tsunami of rules and inferences essentially. So, less the number of predicates we have, the less will be the kind of inferences that we would want to make. So, English verbs and adjectives are just far too many. Now, when we represent things and the phrase that we will use is we will create knowledge bases. So, when we represent things, when we create knowledge bases, we will have some assumptions based on which we will say this is what we know about the world, and the assumptions will be either the open world assumption or the closed world assumption. Do we know the world completely, or is our knowledge of the world incomplete? So, we will have to make that assumption essentially. The closed world assumption says that what you know is all there is to know about the world, that everything that you need to know is being represented. So, it is a little bit like when you have solved problems in school exams, that certain facts are given to you and then you have to show something, and you make the assumption, and the assumption has to be made that whatever you need for showing that that has been done has been given to you essentially. The real world of course is not like that. The real world is there are so many things that we may not take cognizance of, and which may be relevant to what is it that we are trying to show. But the closed world assumption says that everything that you need to know, you know essentially. And very often when we create databases and we create languages like Prolog, we will see that that is what the assumption is under which they operate. A corollary of this assumption is that if you do not know something, then it is false essentially. So, when we look at the language of Prolog, and when we look at this idea of logic as a programming language, we will see this notion of negation by failure. If you fail to show that it is true, then it must be false. Okay. It is not saying that it is false because you do not know whether it is true or false. It is really saying that you have not been able to show that it is true. So, it is negation in the sense of not being able to show that it is true. It is a useful thing to have, which is can be useful in many places. The other assumption is the open world assumption, says that you only have partial knowledge of the world around us, that you know some things, but you do not know some other things essentially. So, should you wait till you have acquired all facts, or can you go ahead and make inferences essentially? Sometimes the world is always changing, and you cannot wait till you have acquired all the facts before you start making your inferences essentially. It reminds me of a story which one of my friends had told me, is that there was a fakir or a holy person sitting by the banks of Indus, and somebody came along and said, "What are you doing here?" So, the fakir told him that I want to cross the river. So, this person asked him, then why are you sitting here? And the fakir says, I am waiting for the river to go by. So, it's like saying that let me first collect all the data and only then I will make inferences. Now, obviously, in the real world that does not happen. So, we are often forced to work with whatever we know about the world, make our conclusions, make our inferences, and if necessary withdraw them at a later point of time. So, the open world assumption, in the open world assumption, the conclusions we make now may have to be withdrawn at a later point of time when more facts come to light. So, this is also sometimes called as non-monotonic reasoning. Which means that what we know and what we have inferred does not necessarily grow monotonically with time. That after some time we may have acquired new facts, in which case some of the conclusions that we had drawn we would have to withdraw essentially. So, we will look at that also later when we look at default reasoning. We will look at this process of making diffeasible inferences. Now, in logic, in first order logic, the domain is a set of individuals and the statements in that logic are relations about those individuals. So, from the perspective of logic, the domain is a set of individuals and the predicates define relations between those individuals. The choice is going to be as to what should be the individuals. From the perspective of knowledge representation, the question is what should those individuals in the domain be essentially. See, logicians do not care about this. They say you give us a domain, you give us a set of predicates, you give us some facts and we will tell you what follows from there. But when we want to build intelligent agents which are reasoning about the some domain, we have to decide as to what should be the individuals that will constitute our domain. As we have said, we cannot represent the physical world as seen by physics, that it is the world is made up of some number of fundamental particles. That level of representation simply does not work essentially, because the number of particles is just far too many. We need to represent concepts in our cognitive model. So, we have said that we have a way of thinking about things which is limited by our perception, and we would like to represent things which are consistent with our cognitive models. So, for example, we may want to talk about the notion of a person, for example, Socrates, and say yes, Socrates is an individual in my domain essentially. But then there are questions that can crop up. If Socrates is an individual in the domain, what about the right hand of Socrates? Is that another individual in the domain? Is that another element in the domain? How is it connected to Socrates? Is it different from Socrates? All these kind of questions will crop up essentially. If you then try to say the hand is one part and Socrates is something and the hand is connected to Socrates, I mean it is a crude way of trying to model the part of relation. Then what about the index finger? Then what about the nail of the index finger? So, all these questions will arise essentially. What is it that we want to represent essentially? Because we would want our knowledge basis to be consistent and we would want our knowledge basis to make all the right inferences. So, if we represent Socrates and his hand separately in the knowledge base and then try to get away by saying that this hand is Socrates' hand or it is a part of Socrates or whatever, then if we make an inference that Socrates has gone let us say to Mesopotamia, then we also have to make the inference that his hand is in Mesopotamia now and things like that. So, that will obviously complicate matters essentially. And if we say Socrates has died, because even Socrates is mortal and he would die someday, even if he had not had that goblet of poison that he was asked to drink. So, if Socrates has died, what about his hand? Then we have to also infer that. So, you can see that representation and reasoning is going to come up with problems like these. And what about things like water, air and sky? Those are things which are difficult to represent as individuals in a domain, because see, water is everywhere. I mean not everywhere, at least it is there everywhere in a river for example, or in an ocean or in a lake or a pond and so on. But it is not an individual, it is not like a glass or a bottle that may be on your table or a pen like this. It is not an individual. I mean even though we have discussed that when we talk about a pen, we have to talk about its parts and so on and so forth. But water is not even like that. It is very difficult to think about water and air and sky. Think about that and we will come back and try to delve a little bit more into how do we choose predicates and what do they stand for essentially.